In this video, we'll talk about the idea of continuity. What does it mean for a function to be continuous? Well, in the informal sense, it means you can draw the graph without having to pick up your pencil. It means sort of a nice function. The graph does nice things, it's reasonable, it behaves correctly. We actually take this and get this towards a more formal definition. Right? If you're drawing the graph without picking up your pencil, that means that wherever the function looks like it's heading at a certain value, that's where the function actually is. So wherever the function looks like it's heading is the actual value at that point. You should recognize this first from our discussions before. This where the function is heading is really a limit. And the value here is the actual function value at that point. So our definition here is that a function f is continuous at a point c if the limit as x approaches c of f of x actually equals the value at c. So this limiting process we've been discussing so far in this chapter gives us the actual value of the function at that point. In particular, this definition implies the limit here on the left exists, the function f is defined at c, and those things are equal. All of those must be true in order for a function to be continuous at a point. Now, what do I know about continuous functions? Well, I already know that some functions are continuous. We already have this substitution principle from doing limits before. This told us that, for instance, for any polynomial, the limit as x goes to c of p of x could be found just by plugging in the values to the polynomial. And the same went for any rational function, provided the denominator was not 0. So what we have from this is that these functions are all continuous. They're continuous where they are defined because rational functions also have issues with their denominators being 0, but at those points the functions aren't defined, so they can't really even be continuous there at all. They have no chance to because they are not defined there. It is in fact this exact property of these functions being continuous that allows us to apply the substitution method to evaluate these limits. So as we do more stuff with functions, you'll see any continuous function, you can just use this method, the substitution method, to evaluate limits. And so once we talk more about continuous functions themselves and what they can do, we'll be able to come back to this and say whenever we want to find a limit, if we know the function is continuous, I can just use the substitution method, plug in the value to get the answer. There's one more extension of this that can be useful in certain circumstances, and that's one-sided continuity. The idea here is that instead of looking at the two-sided limit, I only care about one side of the limit. For instance, a function f is right continuous at c if limit x goes to c from the right of f of x is f of c, and similarly for left continuity. And the big time these become useful is when you're looking at endpoints of intervals. For example, is the function f of x equals square root of x continuous at 0? The issue here is that it can't be, because I'm not allowed to take the limit as x goes to 0 of root of x, because I can't plug in value to the left of 0, because if the value is negative, I can't take square root of that number. So this is not defined, so I can't take the limit of this function that goes to 0. In particular, I can't take the two-sided limit. However, I can take the one-sided limit. So since limit as x goes to 0 from the right of root x does in fact equal 0, we can say this function f of x is root x is right continuous at 0. And that's great. It has no hope of being more than that because I can't deal with the left side, the left-hand limit here, because it's not defined there. To wrap up here, as you'd probably expect, if a function is both right continuous and left continuous at a point, it is then continuous there for the same reason that if I have the two one-sided limits matching, the limit exists. That gives me that idea there as well. So that's the basis of continuity, including one-sided continuity, and how we can talk about functions being continuous at a point based on this definition.